students, today we are going to talk about the lab task this week, okay? So first enter your Canvas and then Modulars Lab 9, and you will find out your task this week from the title of the Lab 9. That is the first one, consolidation test, and the second one, basic skill test number 3, effective stress calculations. So I'm going to post the basic skill test in the assignment part, which will be very similar show in the assignment as the basic skill test number 2. Okay, then back to the modulars. I will post 2 videos in the lab 9, and the first video we are going to talk about 2 examples which will be very similar to your basic skill test. Okay, so now let's start from the first one. For the soil profile showed below, calculate and plot the total stress, the pore water stress, and the effective stress with depth. Use unit of pound per square foot. So in order to simplify this question, I'd like to put several points, which is very important. That can help you to solve this problem. Okay, that is first the point A here. Okay, the point A here, which is at the top of all layers. Okay, and the point B, which is at the bottom of the first layer and is above the second layer. Okay, and the point C here, which is within the second layer and at the top of the second layer and below the first layer. Okay, and the point D here, which is at the interface of the second layer and the third layer, and the point F here at the interface of the third layer and fourth layer, and the point H, which is at the bottom of the last layer. Okay, and there are several equations that I would like to emphasize before we calculate this problem. The first one is how we calculate the gamma D. We use gamma D for the dry soil. Okay, not sand, it's the dry soil. Okay, and we use gamma sat for the saturated soil. That is how we calculate the gamma sat. Okay, and for the moisture unit weight, we calculate it in this manner. And for the S, the saturated degree, we calculate it by the fourth equation. And for the last one, that is the zone of capillary rise, we calculate the pore pressure, which is the suction also in the by this equation. Okay, I'd like to show you another slide about the suction here. As you can see, the suction in the zone of capillary rise, due to the capillary forces, water may rise above the water table. Okay, as you can see, on the water layer, on the water table, the pore water pressure is 0, and under the water table here, we can easily calculate the pore water pressure by this equation, that is H, which represents the depth here. Okay, and the gamma W, which is a constant, we can easily calculate the pore water pressure by this equation. And above the water table, we can calculate the suction in this equation. Okay, so we will see how to apply this equation. Now let's move on to the solution for the example 1. Okay, first let's calculate the 3 values for the point A. As we can see, the point A is at the top of all layers, so the total stress should be 0, the pore water pressure 0, and the effective stress 0 again. Okay, and for the point B, how we calculated the total stress? Yes, it's very easy, is right? So the dry density is given here. It is 103. And depth, we can get it from the figure here, which is 12. Okay, and finally we can get this answer here. And for the point B, how we calculate the pond water pressure? Yes, the pond water pressure is 0 because it is above the water table and it is in the sand layer, and the sand layer do not hold the water. So the pond water pressure should be 0 because it is totally dry. Okay? And then for the effective stress is very easy. We just use the total stress minus the pond water pressure. Okay? And then next, let's continue and move to the point C. For the point C, let's start with the total stress again. So the point C, because it is just above the sand layer, so the total stress should be just the same as the point B. Okay, then let's move to the pond water pressure. The pond water pressure is totally different as point B. Why? Because the second layer, we have moisture content here. That means this layer is not dry. So this layer holds the water. So, however, the water table is under this layer. So based on the knowledge from this slide, we can see that at point C, the pond water pressure is a negative value. And we can calculate the suction, which we called the pond water pressure here. Use the equation here. Okay, so we employed the import the equation of the suction. So we import the equation for the suction here, and we can get this equation. However, we do not know the saturated degrees, right? So we use the saturated degree that we talked at the beginning of this class. Do you remember that? Yes, it's the fourth equation here. And this is W. We got W here. And this is GS. We got GS here. And this is E. We got E here from the figure of the problem. And finally, we can calculate the saturated degree to be 65%. And then we plug this 65% into the equation for the suction. And finally, we can get our answer for the suction. Okay, then the effective stress is very easy again. We just use total stress minus the suction. Is that right? Minus the pond water pressure. Okay. Then let's move on to the point D. The point D is just at the water table. As we can see from this slide, the point at this water table, the pond water pressure should be 0. Is that right? So the pond water pressure here is very easy. It is 0 here. And how we calculate the total stress here? Okay. So to calculate the total stress of point D, we are going to use the total stress of the first layer, which is 1, 2, 3, 6, plus the total stress of the second layer. So how we calculate the total stress of the second layer? We use the gamma moisture. We use the moisture dry density gamma m multiple the depth of the second layer. Okay, so the depth of the second layer we can see from the figure, which is 21 minus 12 equals to 9. And the moisture unit weight we do not know, is not given. So we are going to use the equation here that we talked about at the beginning of this class, which is the third one here. To calculate the moisture unit weight, and based on the value that's given in the figure, we can find out the moisture unit weight, and then we can get the total stress of the point D. And then the effective stress is very easy to calculate, is right? We just use the total stress minus the pond water pressure. And for the point F, okay, the point F for the total stress is we will do it in the same manner as the point D, which the difference is that the moisture unit weight is now become to the saturate density. Okay, so how we calculate the saturate density too? Still, we come to the equation that we talked before at the beginning of this class, which is the second one. Okay, here. We use this equation to calculate the gamma sat to be 112.6 PCF. And then we plug this one into the total stress equation. And then we can calculate the final answer to be 3383. Remember that we need to add this 2144. This one comes from the point D. Okay. Then we are going to calculate the pond water pressure. The pond water pressure under the water table is very easy, as we can see from this slide here. Okay, it's very easy. We just use gamma W, which is a constant, times the depth. We use 32 minus depth of 21. That's the answer should be 11, and we finally get the pond water pressure to be 686.4. Okay, and again, the effective stress is very easy. Okay, for the last point, okay, it's very easy. Again, and gamma sat is given here, okay, and we use it to times the H. The H is now 47 minus 32 to be 15. Okay, then for the pond water pressure, because it is saturated and it is under the water table, so we just use the gamma W here. Multiple the total H, which should be 47 minus the 21, because 21 is the depth of the water table. Okay, and then effective stress is very easy. Now the last step is plot all this into figure. So first we need 3 coordinates. The first one for the total stress, the second one for the pond water pressure, and the third one for the effective stress. And we plot the depths here. It's very easy, right? We just use the value of each point that we calculated before, and then plot each one in the coordinate here. Okay. F, H here. So we are going to draw the line according to the slope. The slope is equals to the unit weight of each layer. As you know the slope of each line, you can draw this line accurately. And for these 2 lines, the unit weight is equals to the gamma W, which is a constant. So this line does not change its slope. Okay, so that's all for the example 1. Then we are going to start our example 2. Okay, the example 2. For the soil profile shown below, calculate and plot the total stress, the pond water pressure, and the effective stress with depths. What is the hydraulic gradient across the sand layer? Okay, then let's do this problem together. Okay, still, let's start from the point A, which is at the top of the all layer. So for the point A, the total stress, pond water pressure, and the effective stress should all be 0. And the point B, I would like set it to be here. Okay. Point B, which is at the bottom of the clay layer and is above the zone of capillary rise. Okay. it is not in the zone of capillarize. So then let's calculate the point B. The total stress of point B is very easy to calculate as the first layer is completely dry. Is that right? So should be gamma D multiple the depth of the first layer, which should be 15 feet. However, the gamma D is not given here, so we need to calculate the gamma D. Okay, remember the equation that we have talked before. Okay, how we calculate gamma D. Okay, we get E and the GS and the gamma W is a constant. Then we can calculate the gamma D to be 101.6. Okay. And for the U here, it should be 0 because the point B is in the first layer and the first layer is totally dry. So the pore pressure water should be 0. There is no water and there is no pore water pressure. Okay. And the effective stress is very easy again. It should be we can calculate the total strength first. We use 101.6 multiple 15, and the answer is to be 1524. Okay, the effective stress should be 1524 minus 0 should be 1524. Okay, then let's come to the next layer. The next point, we'd like to calculate the point C here. Okay, then how we calculate the point C? For the point C, the total stress should be equal to the total stress of point B. Is that right? So it should be 1524 again. Then how about the pore water pressure? Since it is in the zone of capillary rise, so we need to use the equation that we've shown in this slides. Is that right? Okay, this equation again. Then we are going to list it as this one, gamma W H, and the S, we don't know it, so we need to calculate based on the equation of this one. Okay, the water content is 11.9%, and the GS is given here, is the same as the first layer, is 2.66, and the E, it is the same as the first layer, equals to 0.677. So it is calculated to be 50%. Then we can get the function here to be negative 0.5, and the constant of the gamma W, which is 62.4. Okay, and the depth is this part is 15, and the final answer to be negative 468. Okay, next we are going to calculate the point D, which is at the interface of the second layer and the third layer. Okay, how we calculate the point D? Okay, first we start with the total stress. First we are going to employ the total stress of the first layer, which is 1524. We get it from here. Okay. Then we are going to use this one plus the total stress of the second layer. How we calculate the total stress of the second layer? Again, we use gamma M multiple H. Again, The moisture unit weight is not given here, so we are going to calculate the moisture unit weight ourselves. So how we calculate this one? So first we list the equation here. Okay, and we know the GS to be 2.66, and gamma W is a constant, and 1 plus the moisture content to be 11.9%, and 1 plus the and 1 plus E should be 0.633, and the final answer we calculated it to be 113.7. Okay, with this moisture unit weight, we can calculate the total stress to be how much? We use 1524 plus 113.7, and the H to be this part, the second layer, 15, and the final answer turns out to be 3230. Okay, then, and pore pressure, because the point D is at the water table. Remember, the pore pressure, water pressure at the water table is 0. Yeah, so the effective stress should be 3230 minus 0, and final answer is 3230. Okay, we forgot to calculate the effective stress of point C. Okay, it's very easy, so we calculate it very easily here. We use the total stress of point C, 1524 minus negative 468, and the final answer to be 1992. Then there is only the last one here for us is point E left here for us to calculate it. Okay. Still, we start with the total stress here. Okay. So first we should use the total stress of the first two layers. The answer, according to the previous calculation, should be 3230. Is that right? And then we use this one plus how much? Plus the gamma set, which is given, multiple the H, which is 50 feet here. And the answer of this part should be 9080. Okay, and how about the pore water pressure of the point E? As we can see, there is a standing pipe here which shows the pressure head of point E. So here we use pressure head multiple the gamma W to calculate the pore water pressure of point E here. So the gamma W is still a constant, and the HP should be this part 50 and this part 20 and this part 23, and the final answer to be 73 multiple gamma W, and the answer to be 4555. And the effective stress of point E is 9080 minus 4555, and the answer to be 4525. Okay. Okay, then we are going to plot our answer in these three coordinates here. Okay, so let's start with point A. Point A should be all 0. Here, 0. A here. Okay, and then let's move on to the point B. The total stress of point B, we can get it from here, is 1, 5, 2, 4. This is the line, okay? And the pore water pressure of point B is 0 here again. Okay, and then the effective stress of point B Okay, it's the same as the total stress of point B, 1, 5, 2, 4, B here. Okay, then let's move to the point C. Yeah, it's just under the point B. Okay, so the total stress should be the same. And the pore water pressure is much different from the pore water pressure of point B. It's negative. It should be 4, 6, 8 here. Is right? Okay. Then for the effective stress of point C, we calculated it as 1992 here. Okay, then let's move to the point D. Point D, we calculated the total stress as 3230. Okay. And the pore water pressure of point D, because it is on the water table exactly, so it is 0 again. Okay, and the effective stress should be equal to the total stress. Another 3230. Okay. And the last point, point E, the total stress for the point E is 9080. Yeah, we calculate at this. We plot it at this, okay? And for the pore water pressure, we calculate it as 4555. Yeah, we plot it as this. And for the effective stress, 4525 for the point E. Oh, I'm sorry, this is not right. Okay, then we connect each point. For the total stress, we have connected all the points. And for the pore water pressure, we connect A and B, and B and C. Then from C to D, and D to E. And for the effective stress, we connect it from A to B, B to C, C to D, D to E. Okay, let's solve the last problem of example 2. That is, what is the hydraulic gradient across the sand layer? Okay, so first let's recall how we calculate the hydraulic gradient. That is the I equals to the delta H over delta L. L is the distance and the delta H is the head loss. Okay, so okay, the sand layer is here. The head loss is very easy. Let's assume that this layer should be the datum here, and the total head here should be 50, and the total head here should be 73. Okay, then the head loss should be 73 minus 50 over the distance. The distance is this part, it should be 50. So this should be 23 over 50 and equals to 0.46. You will get a very similar problem as these two examples in your basic skill test. Okay, so if you have any question of the basic skill test, you need to repeat this video and find how I calculate these two examples. Thank you. That's all for these two examples.